Number 1, for the standard cell potentials given here, determine delta G naught for the cell in kilojoules, where we're going to be applying the equation delta G naught equals negative N, where F is your Faraday's constant,
96,480 joules per volt mole. So now we just plug in and solve for G. So delta G naught is equal to negative, the N value given is 2 times 96,480. Now remember that is in joules, so we will have to convert to kilojoules. And then the E given. Since the E is 0, this is 0 kilojoules. For B, again, we are plugging in the values we were given. And I get a value that is negative 83.7 kilojoules per mole. I have 3 significant digits in this value. There are 3 significant digits that were given in my voltage value. For C, I get a value of 235.3 kilojoules per mole, and that is positive. Number 2, for the delta G naught values given, determine the standard cell potential for the cell. Well, now we're going to apply the delta G naught equals NFE of the cell again. This time we're going to be solving for the E naught of the cell. So we plug in what we have, but what we're given is our delta G value in kilojoules. Our Faraday is in joules. So we'll need to convert one of those to the other unit. So solving for E naught of the cell, I get an E naught of negative 0.042 volts. I use 2 significant digits in order to report this because I was given 2 significant digits in my delta G value. Now this time I'm going to convert my Faraday. Still solve for the E naught of the cell. And I get a value, this time it's positive, 0.466 volts. Number 3, we're going to determine the standard cell potential and the cell potential under the stated conditions. So for A, I have some mercury and sulfur, and they actually stay in the same half reaction here. And one of the ways you can double check that is by consulting the standard reduction potential table within the classroom. And this one that is more comprehensive than the one that's found in the lesson is actually by element. So if we scroll down, here's my mercury stuff. So here's my mercury and sulfur compound with 2 electrons forms mercury and sulfur. And that has a standard reduction potential of negative 0.70 volts. And then for my other side, I have 2 silvers forming 2 silvers, 2 electrons, and that reduction potential is 0.7996. So the E naught of my cell, this is my reduction, therefore my cathode, and this is my anode. So the E naught of the cell is going to be 0.7996 minus a negative 0.70 to come across the E naught of the cell to be 1.497. Now, I'm aware that that's a few too many significant figures, so I'm not going to round until the end. So the problem, again, asked for the standard cell potential, and that's right here, as well as the cell potential under the stated conditions. Now, in this case, in the case of A, we have two different concentrations here. So I need to find Q. Now, Q, related to the K value, we set it up the same way. So my overall equation is actually given to me. I'm just going to write that out briefly. And I'm going to put the concentrations below. Now we can set up our Q. Q is going to be products. We don't have any concentrations of products, so it's going to be 1 over reactants. Now the concentration of my reactants is going to be raised to the power of the stoichiometric coefficient. So I'm going to have my 0.10, but then I'm going to have my 0.25 squared. So when I go to calculate my non-standard cell, I start with my standard cell, and then I subtract my non-standard adjustment. Make this occur, we see the 2's right here, and I need to take the log of my Q. Now I just wrote out my Q over here. Now be careful with this in the calculator and take it stepwise if you need to. But this should come out to 1.43, and because that's positive, this is spontaneous. So moving on to number 4, we'll follow a similar pattern where we'll write out the half reactions, calculate the standard cell potential, and then the non-standard conditions. So here we're given the words: a galvanic cell made from a half cell consisting of an aluminum electrode in aluminum nitrate. So we're making aluminum 3 and it's at 0.015 molar. And a half cell consisting of a nickel electrode in 0.25 molar of a nickel 2 solution. So we aren't told what is the cathode and what is the anode, but we can figure that out. So we'll go back to our table. I'm looking for aluminum and nickel. So aluminum is going to be towards the top. So here's my aluminum line, and it's a negative 1.662. And nickel, and I'm looking for nickel 2. Here it is, a negative 0.257. Now the E naught of the cell is going to be the anode, or excuse me, the cathode minus the anode. So which is going to be our anode and which is going to be our cathode? Well, remember, the more positive, the more likely to be the cathode. So in this case, we're going to call this one the cathode, and this one is going to be the anode. That means this one will be oxidation, and this one will be reduction. So when we write this out, the overall reaction, we'll write our nickel out as reduction, and our aluminum as oxidation. We're going to need to multiply both of these by a factor in order to get the least common multiple. And then the moles of electrons we will use for each side our N value will be 6. So the E0 cell value is a positive 1.405 volts. So now I can calculate my non-standard cell and my aluminum. I'm going to drop these concentrations down too so we can see those. So my non-standard cell, I start with my standard, and then I subtract, and my N value is 6, that's why there's a 6 there, log of the Q value. Now the Q value is going to be products over reactants, and here my product is squared because that's the stoichiometric coefficient in front of it, and my reactant is cubed. So when you put all of this in the calculator, you should get a non-standard E cell value of 1.423 volts. So it was spontaneous at standard conditions, and it is spontaneous at these as well.